Hello again. Now this is a little bit dodgy because there are parts of this I don't want to do until Tuesday. So I've covered up those parts, very makeshift, but it's okay. The key thing for this section is here, and I don't know if you've even got these boxes, so because you've got the dodgy notes, I would write this out, leave a bit of space for what's underneath this piece of paper. Again, on the other page as well, you might have wanted to written something down that might not have been printed in your notes. I would strongly advise that you do that. Now, as we looked previously at increasing, decreasing functions, a function is either increasing or decreasing, except for when it is neither increasing or decreasing, so at a stationary point. So the tangents to a curve where we have a stationary point are horizontal lines with no gradient. And so as a result of that, when we're looking at identifying where the stationary points are, we would do that. We would take advantage of the fact that the gradient is 0 at those points. So by solving dy by dx equals 0, we can work out the location of the x coordinates of the turning points, and then in turn find the y coordinates. Now, here are the notes. So find the coordinates of the points find the coordinate of the turning points on the curve y equals x cubed, take 3x squared, add 4. Now, again, we would find dy by dx and set it equal to 0. So we've got 3x squared take 6x equals 0, Solve that using calculator or just factorising if it's easy. We've got 3x equals 0 or x minus 2 equals 0 to give these solutions to that quadratic. So those are the x coordinates of the turning points, because those are the x coordinates that have a 0 gradient. We've specified that the gradient is 0, and those are the points where that is the case. Then we want the coordinates of these points, so we can't just settle for x values. We must substitute those into the original function. It's a more common mistake than you might think that people would then substitute those values back into the dy by dx, and they wouldn't even notice that they were obviously going to get 0. You must put those numbers back into the original function to get the corresponding y coordinates. Okay, remember, dy by dx is all about gradients. The original function is about the link between x and y coordinates and points, basically. Okay, so next question, same thing, but we're ignoring the determine their nature part underlined in red, and that's the bit that's covered up by that piece of paper. We will come back to that on Monday, and you will get a chance to fill that in. But for now, we're just going to identify and locate the turning points. So again, we'll begin by differentiating, because we know that the gradient at the turning points is going to be 0. So we differentiate to find dy by dx, set that equal to 0, and solve. I just used my calculator, it seems here. We've got x equals 1 or x equals 3. And so those are the x coordinates of the turning points, and we've got y is 5 and y is 1 that correspond to those points, and then we would round that off by just saying that the turning points are at these points, bringing it all together. Okay, so that's that. Oh god. Right, okay, so next two examples, again, shoddily covered up the bit that you don't need, but with a piece of paper. This is a little bit trickier, but not, we shouldn't worry about it too much. We first need to get it differentiatable, like so. We would then differentiate to find the gradient function, and that's that. Now, because I specifically, in fact, you can ignore that as well. Because I specifically want the turning point, and that's when the gradient equals 0, it's going to be easier for me to rewrite this back in fraction form, because then I can times things across. When I've got this equation here, I can times things across. It's not immediately obvious how you would have solved that equal to 0. So manipulating it back to something that's a bit more manageable is a good technique and something you should be able to do. So as we know, turning point, the gradient function equals 0. Because I've put it back in this form, I can multiply across by the x squared because the fraction's annoying me. That would give me 2x cubed, remember, equals minus 54. I've actually skipped a step there. It would go to 2x. It would go to 2x, add 54 equals 0, 2x cubed. I would prefer that step in there and then take the 54 over to the other side. And then you can say that x equals minus 3 by solving that. So this curve only has one turning point at x equals minus 3. And so the y-coordinate when x equals minus 3, putting it back into here, gives us 27. So here we have a turning point at minus 3, 27. Again, just ignore the determine whether it's a maximum or minimum. Now, let's move that piece of paper. You should have this question here. Again, bottom question, we're not going to do, but we've got this question. In fact, we're going to ignore this table for now as well, so don't worry about that. We're just doing the bit in red. So we've got this curve, it's a trig curve, but it shouldn't be, it's just emphasising the fact that no matter what function you have, the process for finding stationary points is always the same. You differentiate and you make that equal to 0. You solve that, you get the x coordinates of the turning points. Then you find the y coordinates that correspond. It's that straightforward. Now, I'm not saying it will always be straightforward to do the solving and the differentiating, but the process is always the same. Now, dy by dx here is half add 2 sine 2x. You should know that by now, because cos differentiates to minus sine, and we use the chain rule because it's got the 2x in there. Set that equal to 0, like so. Rearrange and solve. Now we've got a 2x here. We've got a 2x here, and so we have to use this method of doubling the domain, and you can see how we follow that through. So you get solutions for u. Some will be acceptable, some will not be. And so there are acceptable solutions for our domain are 3.015 and 1.695, and we've substituted those back into the original function to find the corresponding y coordinates. Now, I would like you to copy all of that out for the 3 videos. There'll be work to follow. I would also appreciate if you let me know whether the quality of the video is too blurry, basically, because I'd just like you to pause it and copy it out, but if absolutely necessary, I can photograph the relevant parts. Alright, I think that's all the stuff we'll do for today. I'll send to back these videos up the relevant links to that guy, Jack, his videos, just for another perspective potentially, or further examples. There'll definitely be further examples in his videos, but then if that's not necessary, you can just crack on with the independent study. Alright, have a good weekend as best you can.